Welcome to The Explainer. Ever wonder what's really going on deep inside your phone, your smart TV, or the servers that basically run the internet? Well, today we're going to peek behind the curtain at the digital brain behind it all, the Linux kernel. To do that, we've got to learn its unique language. It's how we'll understand the way it works, who actually builds it, and why it's one of the most important pieces of software ever created. You know, this quote from an early kernel guide just perfectly nails the whole spirit of open source. It's not about having all the answers right from the start. Nope. It's about people seeing a problem or a need and just diving in, building the knowledge together as they go. That collaborative spirit is exactly what makes the Linux kernel possible. And we're going to see it in action today. All right, here's our roadmap. First, we'll get the basic language down. Then we'll see how the kernel juggles a million things at once and actually talks to your hardware. After that, we'll meet the global community that builds this thing, and we'll wrap up by looking at why all of this really matters for the devices we use every single day. Okay, let's get into it. The best way to understand the kernel, really, is to think of it as a huge, bustling city. It's got traffic, it's got infrastructure, and it definitely has its own unique language. So, to get around this city, you've got to know the local lingo. I mean, the sheer scale of this project is just mind-boggling. We're not just talking about some code. This is a massive, ongoing human endeavor. In just one 3-month window, you've got over 1,000 developers from more than 100 different companies all working on it. So this shared vocabulary we're talking about, it isn't just helpful, it is the essential glue that lets all these people build and maintain this digital city together. So how does this digital city manage all its traffic, right? How can you browse the web, listen to music, and have a file downloading all at the same time? Let's look at the core concepts the kernel uses to juggle all of these tasks. Okay, so the most basic unit here is the process. If our kernel is the city, you can think of a process as a single car on the road. When you open your web browser, that starts one process. Your music player, that's another process. Each one is its own little self-contained task that the kernel has to manage. Now let's look inside that car. If your browser is the process, a thread is like a passenger inside, doing a specific job. One thread might be loading the images on a web page, while another is playing a video on that same page. And a third is just waiting for you to click your mouse. By splitting the work up into threads, a single app can feel like it's doing many things at once without just freezing up on you. So how does the real world, your keyboard, your mouse, get the kernel's attention? Well, that happens through an IRQ, which stands for interrupt request. And you should really think of it as an emergency siren. The moment you click your mouse, the hardware sends an interrupt signal. This forces the CPU to stop whatever it was doing, I don't care how important it was, and immediately handle that mouse click. It's the system that makes your computer feel instant and responsive. All right, let's head over to the next district in our digital city and see how the kernel translates all your clicks and keystrokes into actual actions in the physical world. This is all about the conversation between the software and the hardware it's running on. Every single piece of hardware in your computer, your graphics card, your Wi-Fi chip, your webcam, each one needs a personal translator to speak the kernel's language. And that translator, that's the device driver. Its job is to take a generic command like draw a window and turn it into these super specific instructions that only that particular piece of hardware can understand. And this is where it gets really interesting. The driver that lives in the kernel isn't the only piece of software involved here. A lot of modern devices, like a Wi-Fi card, have their own tiny little operating system built right into them. We call that firmware. And it's often the kernel's device driver that's responsible for loading this firmware directly onto the hardware just to bring it to life. Okay, so let's be super precise here because these two terms get confused all the time. Firmware is the whole package. It's the binary file that the driver loads onto the device. You can think of it as the complete instruction manual. Microcode, on the other hand, is the actual language inside that manual. Those are the super low-level commands that the device's own little processor understands. So the driver delivers the firmware, and the firmware contains the microcode. You know, the kernel isn't just lines of code. It's a massive social system. It's built and maintained by thousands of people all over the world. So let's take a look at the language they use to collaborate, to build trust, and to make sure this whole global project actually works. A project this huge has to have a clear structure. At the bottom, you have contributors. That can be anyone submitting a change, even a typo fix. Their work then gets checked by reviewers, who are trusted experts in one specific area. And at the top of that food chain are the maintainers. They are the ultimate gatekeepers for their part of the kernel, whether that's graphics, storage, or networking. So every single change, which is called a patch, goes through a very public process. As it moves along, it collects these little digital sign-offs that build what's called a chain of trust. It starts with a signed-off by from the developer, that's basically a legal certification. Then it might get a reviewed by tag from an expert, an act by from a maintainer giving the final green light, and ideally a tested by tag from someone who actually confirmed it works. This public record is how you maintain quality with thousands of people contributing. Okay, so we've learned some key terms about how the kernel works and how it gets built, but what's the ultimate payoff here? Why go through all this trouble? Why does this all matter? Oh man, this quote gets right to the very heart of it. This is the magic of what's called the mainline kernel. By getting your code into the official version, you're not just contributing. You are plugging your work into a global maintenance machine. It means when the kernel changes and evolves, thousands of other developers help make sure your code evolves right along with it, basically for free. So, what does this shared language really make possible in the end? It creates a system where thousands of developers can pretty much act as a single coordinated mind. It's a foundation that's built not on rigid control, but on shared understanding and a whole lot of trust. And as our world gets more and more connected, maybe the biggest lesson from the Linux kernel isn't really about code at all, but about how we can collaborate. Thanks for joining me.